How much time we have. All right, so today's in the news segment. Hopefully you guys have heard about, some of you might have heard about the new movie Moneyball. Some of you guys might have seen it. And that's a problem with handing things out late. Okay, so I need you guys to calm down a little bit. So you might wonder what it has to do with 61C. Other than the fact that Brad Pitt is in it, and he, as you know, was one of the better 61C students a number of years ago. It's about the A's. Right, and it's about the Oakland A's. But the reason I picked this one, is if you know the story about Moneyball, it's a story about how the Oakland A's, through basically providing or looking at the right performance metrics, figured out a way to build a very competitive team at a small fraction of the cost that other teams were spending. And the reason they did that is because they had a bunch of data, and they realized after looking at the data that the things that those other teams were valuing and what they were paying players based on weren't necessarily the most important things for what makes a good player in a winning team. And so the most famous thing that came out of here, if you follow baseball, is that batting average turned out to be kind of a crummy metric for hitters, even though everybody uses it. And it turns out that on-base percentage, which includes walks, is actually the thing you want to measure. And a couple other things like that. So if you get a chance in between projects, in between studying for the midterm, you might want to go see the movie or at least read the book or both. And that'll inspire you to see how having a good understanding of metrics and understanding performance can really make a big difference. Okay, so that's in the news. All right, so what we're going to do today, we're going to finish up the discussion on direct map caches, and then we're going to basically go into some details on caching in general and how caching impacts performance. And then on Wednesday, we'll do one more caching lecture. We'll talk about a couple advanced topics with caches, and then we'll be done with this part of the class. Okay? And as you know, we're heading in towards the midterm. The midterm is next Thursday, so a week from Thursday. And we'll tell you more about that probably next class. The other thing I should mention is my office hours are Tuesdays at 10, and they're in Soda Hall, in 465 Soda Hall. Or if I'm not there, there'll be a sign saying where I am. We're still trying to find rooms. Okay. All right, great. So here's where we left off last time. When you so caches are all about trying to hide the fact that you've got this huge slow memory and you've got this fast processor that doesn't have much storage to work with, and so you're trying to bridge that gap. And so what we're going to do is we're going to bring things into the cache when we need them, and hopefully even a little bit before we need them, okay? And we're going to use them out of the cache, which is very fast. And when we need something that's not in the cache, we're going to go get it and bring it in, possibly kick something out. So part of what you need to do is to be able to tell when the processor issues a request for an address, is the data at that address in the cache or not? And so the way you do that is by looking at the memory address, okay? And, do you have your yeah, okay, great. The way you look at the address is with this acronym TO, which basically says the highest order bits are the tag, the lowest order bits are the offset, and the middle stuff is the index. Thank you, sir. And, all right, great. And, basically, what the offset bits tell you, the cache is divided into blocks. The offset bits tell you where in the block that particular byte is located. The index tells you which block or which position in the cache that address would be if it were in the cache. And then the tag is in the address, and it's also replicated in the cache itself. And what you do is when you're looking up an address, you look in the cache position indicated by the index, and then you check to see if the tag is the same as the one in your address. If it is, that means that the location that you're looking for is in the cache. That's called a cache hit. if the tags differ, that means it's not in the cache. It means something else is there. That's called a cache miss. Okay? All right, so I didn't show you this picture, I don't think, last time. But this is a 1024 entry cache. And basically, we've got the data, which is the actual piece of memory that we're storing in the cache to have it close by. The tag is what I just told you about. And then a valid bit, just 1 or 0, tells you if it's set to 1, that means the thing that's in that cache position is a real cache entry. If it's 0, that means it's just garbage. So when you initialize the system, when you first bring it up, all the valid bits in the cache are set to 0. And as you bring things in, those valid bits get set to 1. Okay? So this example, our cache block is 1 word, okay, in size. So a word, we're going to say a word is 4 bytes. So each block has 4 bytes of data, and there's 100K words. Okay, so it's a 4 kilobyte cache. So your processor is running. It needs something from memory. So it presents this 32-bit address. So what is that address going to be? All right. Well, because we have 4-byte blocks, that means we need 2 bits as an offset. So our least significant 2 bits are going to represent, the bytes 0, 1, 2, and 3 for that block. Okay. We have 1K entries in the cache, so that means we're going to need 10 bits to represent the index. Okay? So we're going to look at these 10 bits. We're going to ignore the first 2. We're going to look at the next 10. That tells us which entry in the cache that this guy is going to be located at if it's in the cache. Okay? So that points us to an entry in the cache. The rest of the bits are the tag. Okay? And so there's 20 left. So then what we do is we say, okay, our address has these 20 bits. We look in the cache entry, and we see if the tag has the same 20 bits. And we also check to see if the valid flag is on. So if the tag in the cache line equals the tag in the address, and the valid bit is set, then that's a hit. Okay, so hopefully you've seen this before. This is an AND, right? Just a logical AND. So if this equality evaluates to true, and the valid bit is set to 1, this is a hit. Okay, it's pretty much that simple. Okay, and if it's a hit, then the block, the 32-bit block that we're looking for, is what's stored in this data address. So we send that back. We send that back to the processor. Okay. So that's a direct map cache, and the question here is what kind of locality are we taking advantage of here? Remember, we have 2 types of locality that we can use, right? Locality is that principle that tells us at any time we tend to access only a small amount of all possible memory, right? Temporal locality tells us that things we've accessed recently we're likely to access again soon, okay? And spatial locality tells us that things that are near what we've recently accessed are likely to be accessed soon. Okay, so one is based on time, one is based on proximity, okay, in space. And the question here is, what kind of locality are we taking advantage of here? And the answer is a little tricky. So the main thing we're taking advantage of is temporal locality. Okay, so if you access this word of memory, okay, it's going to be brought into the cache the first time. Okay, if you access it again, it's there. Okay, and temporal locality says you're likely to access it again. That's what temporal locality is about. Okay, now you might ask yourself, what about spatial locality? Why isn't this taking advantage of spatial locality? And that's the part that's a little subtle. Okay, because in the MIPS architecture, you basically go to the memory word by word. Okay, so basically your access to the memory is a word. Okay, now within that word, you might look at this byte, then this byte, then this byte, then this byte. So there is a small amount of spatial locality going on here. Okay, if you're looking at things bit by bit or byte by byte. But by and large, a request to the memory is a word, so you bring in that word, and that's your unit of access. And so that's why the idea here is that this is mostly about temporal locality. Okay, I'll show you spatial locality in a second. Question? Yeah.
Isn't it also spatial locality because, like, you're assuming that the block later that's going to go into the same place in the cache is not empty?
I'm not sure I understand. Sorry.
Like, since that can be replaced by a different block from memory, but you assume since those two blocks are far away from each other, it won't be replaced.
We're using sort of the anti-spatial locality. Even that is about... Right, I guess that's probably true, is it? Yeah, okay, sorry. So there's a little conversation going on up here. So the question is a really interesting one, which is why we're having a conversation, which is, aren't we sort of taking advantage of spatial locality because the things that are going to be near this address in the address space are actually going to map to different entries in the cache because the tag is these lower bits. Okay? I'm sorry, thank you. The index is these lower bits. Okay? And so that's true. There is a sort of a secondary effect that way, that if you were to just sort of march through memory, you know, the next word of memory wouldn't map to this entry, it would map to this entry. And so you'd keep that first one around. So there is a little notion of spatial locality here. And if you weren't worried about that, then you could easily have the index as the high order bits. But then you'd potentially get into that trouble because all the neighbors would end up in the same entry in the cache. So that's a really good point. Okay. All right, that's a good exam question was the comment that somebody in the first row made. Okay. All right, so let's look at this thing in action now. Okay, so I showed you sort of the static version of it. So here's a sequence of memory accesses, and we'll just look at 4-bit addresses here for a minute. So we're going to look at block 0, then we're going to request block 1, then 2, then 3, and so on. Okay? And to keep myself from getting confused and you guys from getting confused, I put the binary there. All right, so we start off with an empty cache. Initially, everything's marked as not valid. Okay, and we request 0. So we request 0, we look in the cache. That should be in that first line, in that first entry, because we're doing 1-byte words. So if you have 1-byte words, you don't have any offset, right? Because there's nothing to distinguish about within a block, because there's only 1 byte there. So the tag is going to be, how many tag bits do we need here if we have a 4-line cache? We need 2 I said tag. Index. I keep doing that, sorry. How many index bits do we need to index 4 lines in the cache? We need 2 bits, okay? So the index is going to be the least significant 2 bits. So 0, if it was in the cache, would be at location 00, which is this first one, okay? But there's nothing there. It's marked not valid, so that ends up being a cache miss. And we have to basically go out to the memory and bring it in, okay? So go out to memory. As you know, that's like, going to Sacramento and driving back. Finally, we come back and it's sitting there in the cache. Okay, it didn't help us this time, okay, but temporal locality tells us it might help us in the future. Okay, great. So now let's go our next request, block 1. Okay, likewise, that's not in the cache, right? That should show up at index 1. It's not there, so we're going to read that one in. Okay, that's a miss. Then we go to the next access, that's 2. All right, what's going to happen there? Well, that's going to be in entry 2, but entry 2 is empty. So that's another miss. Bring that in. You can see this. We did a lot of work on caching, and how much has it helped us so far? 0, right? Okay, well, maybe things will get better. Let's go for 4. Where should 4 be? Well, 3. Okay, I'm okay, man. So 3 should be here. Okay, but there's nothing in there. So that's going to be another miss. Okay, boy, this is really getting bad. Finally, we're going to get to 4. That's going to be great, right? So we go to 4. Okay, well, 4, okay, where should 4 be? Well, 4 should be at position 00. Great. Hey, look, there's something in position 00, but it's not 4. Okay? So that's a miss. Even though there's something in there, we miss. Okay, so that's a miss. What do? Well, we have to go get item 4. We bring that in, and when we bring that in, we clobber what was in that position before, okay? So that's why you can see now the tag is 01, and the thing that's in the block is the data for 4, okay, location 4. Okay, now we're going to go for 3, okay? So we're marching along our sequence here. Okay, 3 should be in location 11, okay? Let's look at location 11. Hey, look it, good news. That's a hit, that's our first hit, okay? So now, instead of having to go to Sacramento to get that data, we return right away. It's right there. Okay, that's the benefit of having a cache. Okay, now we're going to go for 4. Is 4 going to be a hit or a miss? Yeah, it's a hit. Great. Okay, good. So now we seem to be on a roll. Okay, and then 15 is our last request. What's going to happen with 15? Where are we going to look for it? It's going to be in position 3. What's in position 3? Well, unfortunately, not 15. So that's a miss, and we're going to have to bring in 15 and wipe out whatever was there, okay? So how did we do with our cache, right? We did all this activity. We did all this work. We made 8 requests. We had 6 misses and 2 hits. That's a 25% hit rate, or conversely, a 75% miss rate. Yeah, question? All right, so the question is, when we access one of them, why don't we load a bunch of them? And that's going to be what spatial locality is going to do for us. Okay? So the thing is, the processor is sitting there getting requests, and it actually doesn't know what requests are going to come next, right? So it can't know with certainty what you're going to ask for next. Okay, so it makes an intelligent guess. Okay? Now here, the way we set it up, our cache only holds individual bytes. So it's actually not even a very realistic example. We can only get a byte. This is an example that says we can only get 1 byte from memory at a time. So we don't really have the option of getting more than one thing, but I'll show you how we're going to address that next. Yeah? In the previous... Yeah, in the previous example, the size of each block, the amount of data you store in each entry was 32 bits. There's 4 bytes. So that's why we needed 2 bits as an offset. Here, because each one is a byte, you don't need an offset. When you get to a cache block, there's only 1 byte there, and it's the one that your address is pointing at. Okay, so the size of the data entry in a block is 2 to the number of bits in your offset. So we only have 1 byte, so 2 to the 0. That's why we have 0 bits in the offset. Yeah?
We also needed 33 bits for the cache part of it, right? Like if we're storing 32 bits and the address is 32 bits, then we need 1 bit for a valid bit.
Yep.
Then we have 65 bits total to use in the cache to store 32 bits.
Right, okay, so this is a good point. So the point was, if you look at the amount of storage in the cache, so I said it was a 4 kilobyte cache, okay? And 4 kilobytes was the amount of data. I kind of hesitate. Let's see. Let me just go back there just so that I'm not gesturing into the sky here. Okay, so let's go back to this example for a second. Okay, so the comment was, okay, this is a 4 kilobyte cache, okay, and 4 kilobytes is the amount of data. So that's how much memory you can cache, right? So you've got, 256 gigabytes of memory, right, main memory. You're allowed to make copies of 4 kilobytes of it in this cache. Okay, but the comment was, but if you look at the cache, it's actually bigger than 4 kilobytes. And that's true because the size of each entry is more than just the data. All right, I've got 1K entries. I've got each data block is 4 bytes, but then I've got the tag, which is 20 bits, okay, and I've got the valid bit, which is another bit. So I'm actually, the size of an entry in the cache, in this case, is 53 bits, okay? And in that 53 bits, I'm actually storing 32 bits of data. Yep, okay? So any other questions about that stuff? Yeah. I'm sorry? Okay. Ooh. All right. So why is the tag 20 bits? All right. Well, we've got 32 bits. The data region is 4 bytes. Okay. So any address is going to point to an individual byte. Okay. So in order to tell which byte of these 4 you're interested in, you need 2 bits. Okay. 0, 1, 2, and 3. Okay. So that's the offset. So we lose 2 bits for the offset. Okay, the index, we need enough bits in the index to distinguish uniquely which entry in the cache there is. Okay, and in our cache, which you can barely see here, we have 1,024 entries. So you need 10 bits to be able to uniquely identify which entry in the cache. That's the index. So that's 12 bits altogether. It's a 32-bit address, so we get 20 left over for the tag. Okay? And you need all 20 because if you didn't have all those 20, you couldn't tell the difference between 2 addresses. See? Okay. Any other questions on this? This is all the lead up to, or actually the finish of what we were doing last time. Okay. So in the previous example, I showed you just, this very kind of unrealistic case where each data item only holds 1 byte, right? So each entry only holds 1 byte. And somebody in the back asked a great question, which is, well, when I'm taking the trouble to go all the way to Sacramento, why should I come back with just a single byte? Okay, that seems dumb, especially in the case that I just showed you where we had a lot of temporal locality and spatial locality. We were walking through a sequence of addresses that were all near each other, so spatial locality. Then we looped a little bit, so that's temporal locality. Okay, so let's say we wanted to take that suggestion and design a cache that worked that way. Okay, so instead of having just 1 byte as our data in the cache entry, let's have 2 bytes. Okay, so let's just double it. So that's what this is showing. Now, so instead of having 4 entries in the cache, 1 byte each, right? We want to be able to cache. We're still going to have a 4-byte data cache. This is really a dumb example. So since each entry is going to hold 2 bytes, we only need two entries instead of 4. Okay? So now the way we're going to be looking at our addresses is how? Okay, well, each entry is 2 bytes. So we need to know, are you interested in byte 0 or byte 1? So that's going to be the first bit, right? The low order bit is going to be our offset. So we have an offset of 1, right, because we're choosing between 0 and 1. Okay? We have 2 entries in the cache. So how many bits do we need for an index? Yeah, just 1, right? Because it's either going to be entry 0 or entry 1. And then the rest is our tag. So we got 2 bits left over for the tag. Okay? So roughly the same amount of storage, okay, as before. Okay, except now we've split it into 2 cache blocks of twice the size instead of 4 cache blocks of half the size. Okay? So we're still caching the same amount of data from memory. All right, now let's see how this one works. Last time we got a 25% hit rate. Okay, so we access 0, cache is empty, that's going to be a miss. Okay, but we're going to read it into our location, which is specified by that. So that 0 is our offset, and then the second bit, 0, that's our index. Okay, so we're going to write it into index 0. Okay, and when we bring that data in, not only do we bring in 0, but we bring in the byte next to it, which is exactly what you wanted. Okay, so we're bringing in bytes 1 and byte 0. Okay? Okay, cool. So now let's access byte 1. Let's go to the next one. Okay, well, where should byte 1 be? You look at the index, that says it should be in location 0. Hey, sure enough, at position 1, there it is. Okay? So that, which in our previous cache was a miss, is now a hit. Okay? That, ladies and gentlemen, is spatial locality. That's spatial locality. It says, I was at 0, chances are I'm going to go to 1 next. Why don't I just bring them both in? Okay? Cool. Okay? How about 2? That could help. Well, 2 is going to be a miss, okay, because 2 is not in the cache. But we're going to bring it in, and when we bring it in, we'll also bring in 3. That's going to be convenient because what do we access next is 3. So we're going to get another hit. Okay, so we're 50-50 so far. That's better than 25%. Pretty happy. Okay, now what happens? We access 4. That's the next thing on the list. So 4 should go into position 0. Unfortunately, when you look up the tag, 4 has a tag of 0, 1. If you look in position 0, what you have is a tag of 0, 0. So even though there's something in the cache at the position we're looking for, the tag tells us it's not the thing we're looking for. So we have to go out and get 4, and we bring it in, which means we're going to clobber what was there before. So that's a miss. Access 3 again, that's still in the cache. That's a hit. We're happy about that. Go back to 4, right? This is temporal locality, right? Because we just accessed 4, that brought it into the cache. Now we're going to access it again. Guess what? It's still in the cache. So that's going to be a hit. And then when we access 15, we haven't touched 15 yet, so that's not going to be in the cache. So where's that going to go? Well, index 1. So it's going to go into position 1, and it's going to have a tag of 1, 1. So we're going to put that. That's a miss. And that goes in the cache with the tag of 1, 1. Okay, so 2 cases. This is really important. 2 cases. Both were able to store 4 bytes in the cache. Just by organizing it slightly differently, we didn't add any address bits. We didn't, it's still 4-bit addresses. We just looked at them a little differently. Okay? We went from having a 25% hit rate to doubling that. We now have a 50% hit rate. Half the time we make an access to the cache, what we're looking for is there. In this particular example, half the time it's not, which is better than before. Okay? Because before it was only 1 out of a 4 chance. Yeah?
How much is it going to slow down since we're now getting 2 bytes instead of 1 byte?
Right.
How much will that slow it down?
Okay, great question. So the question was, now that we're getting 2 bytes instead of 1 byte, how much is that going to slow things down? And the answer is, it depends on your architecture, and it depends on how wide the bus is and all that. But in general, the bigger your cache blocks are, right, the more data you have to fetch every time you have a cache miss, the slower that's going to be because you're going to have to get multiple requests from the memory. Okay? So if you look in the book, in one of the expanded sections, there's actually a discussion of how you can try to mitigate that problem. So, you can have systems where even though you're filling up the cache, as long as the piece that you're looking for, based on what the offset tells you, comes in, then you can start the instruction. And you can also have sort of parallel architectures that make things go faster. But in general, the bigger the cache block, the more you pay for a miss. Okay? So it's not a slam dunk. Okay? It's not, because if you take this example I just showed you to the extreme, you'd say, okay, well, I know what I'm going to do. I'm going to have 1 cache block, and it's going to be the size of the entire cache. Wouldn't that be better? I don't know. Would that be better? No, yes, no, maybe. The correct answer is maybe. It totally depends on the access pattern, but I would say probably it's going to be worse. Okay, and why is it going to be worse? It's going to be worse because of this one thing we just said, which is the cost of a miss is going to go up because you have to bring more data in from memory. But it's also going to be worse because if you can only store 1 block in the cache, every time you have a miss, it's going to throw out what you have in the cache and bring in something else. So if you just if you're doing a lot of spatially local accesses and you just hop out once, that's going to wipe out your cache. When you come back to your spatial locality, nothing's going to be, the thing you're looking for won't be in the cache. Okay? So yeah.
So in terms of program, and you know some part of it is going to have off behavior in the cache. Is there some way to ever tell it to tell the cache to have a different block size, for example, for some part of the program?
Well, okay, so the question is there a way, if you knew or the compiler knew that you were going to be doing something weird in your access pattern, is there a way to tell the cache that? And then you can correct me if I'm wrong. But I think the answer is in general no. And the reason is that, remember, all this cache logic is happening in hardware. And you want it to be super fast, super simple, and super fast. So in general, the decision made when people are building out these caches is to find that middle ground between simplicity and being able to handle special cases. And in computer architecture, as in a lot of things, the mantra is make the common case go fast. Okay, so what you want to do is the thing that happens most of the time, you want that to be as fast as possible. And, if there are some cases that are slow every once in a while, you're willing to accept that. Okay? Now, there are things you can do as a programmer. Okay, and in fact, if you look at the next homework, you'll see a hint at one, where if you understand how big the cache is, you can write better code, code that's going to behave better in the cache than if you didn't know how big the cache was. Okay, so you can do that yourself, but in general, there isn't an easy switch at the cache level to say, hey, ignore what I'm about to do or something like that. Yeah?
How long would it take to access cache memory? Is it constant time or is it meter search?
The time to access the cache memory, I believe, is for a cache of a given block size is constant time. Okay? Yeah. Okay, good. So the question is, how do we measure the efficiency of the cache? Why don't you hold on to that question, because I'm going to go over that. Okay? And the answer is yes. It's some combination of, your hit rate and how much it costs when you miss. Yeah?
If you have more than one cache, you have to store additional bits in the instructions to say which cache to go to.
Okay, so question is, if you have multiple caches, do you have to store extra bits in the instruction to say which cache to go to? So there's two ways that you typically have multiple caches. One is you can have caches next to each other, okay? And we talked about that a little bit before. So you could typically have a separate cache for instructions and a separate cache for data, okay? And that's because the access patterns for those two things are very different. And in particular, the instructions you tend to go through linearly with some small loops, okay? And so, you don't want your data accesses messing that up. Okay, so in the case when you have an instruction cache and a data cache, the system knows whether it's trying to fetch an instruction or fetch something from memory, some data from memory. So there you don't have to do anything. The other way you can have multiple caches is if you have, as we said before, a hierarchy. We have a level 1 cache, followed by a level 2 cache, which is bigger and slower, followed possibly by a level 3 cache, which is even bigger and even slower. And in that type of a multiple cache hierarchy, again, you don't have to worry about it. The system's going to make sure that data gets brought up from the highest level that it's in to where it needs to be. Yeah?
Well, wouldn't that be really inefficient with, a lot of your caches would be copied from this stuff?
Yeah, so good. That's a really good point, too. So we're jumping a little bit ahead. But the comment was, if I have that hierarchy, wouldn't that be inefficient because my caches are basically copies of each other? I'm sorry, everything I have in level 1 is also in level 2 in general. And that's very true, except that the idea is that the size differences are so dramatic that it's not a significant portion of the size. So, your level 1 cache is going to be a small percentage of the size of your level 2. So it doesn't matter much. Okay? Yeah, right. And a little voice in my head is telling me that also, you want that stuff to be in the next lower cache, because if you kick it out of the higher level cache, locality tells you you're probably going to go for it again. You want to get it out of the next level. Yeah. Okay, good. So let's look at that same picture now with that I showed you before, but now let's do it with a multi-word cache. So which is this one? This is 256 blocks, 4 words per cache block. Okay. So a word is 32 bits. So I've got 4 bytes, 4 bytes, 4 bytes, and 4 bytes, okay, in my cache block. So I've made this a really big block, okay? Keeping the data portion the same size, that means instead of 1K entries, I now have 256 entries, okay? And I adjust my use of TO differently, right? So I have a bigger offset now, okay? I have a smaller index because I have fewer entries, okay? And then the rest is still the tag. And then what I do is, when an address comes in, I do what I do before. I take the index bits, which in this case, there's 8 of them, because I'm indexing into 256. That gets me to an entry in the cache. I then check the tag. The tag is 20 bits. All right, so I check that. If they're equal and the valid bit is set, that's a hit. And then I return the data. And in this case, I've got 4 words in there, so I've got to determine which word I want, and so I use the offset to do that. So the offset tells me, which word and which byte in the word. Okay, and basically, I typically get back a word at a time. Oh, okay, well, you can figure it out. Okay, so you can see there's 4 words going into here, and there's one 32-bit word coming up. Okay? And the one you're choosing is based on this block offset. Okay? So it works very much like the single block cache that I showed you before, just extended so that we can take advantage of spatial locality. Yeah? Go ahead. Yeah.
How do you get a word instead of a byte?
How do you get a word instead of a byte? Well, actually, it's kind of, you should ask, for MIPS, you should ask the opposite question, which is, how do I get a byte instead of a word? Because, when MIPS talks to memory, it always talks in words. So what you do is you get the whole word, and then you do the byte, the bit level operations if you just need a byte. Okay, so let's keep going. All right, well, there might be an error in that one. I don't know. But let's go. All right, so is it 2-bit offset? Okay, so there's 16, so we got 4 bits. We got 4 words, 4 bytes each. Yeah. Yep. Yeah, definitely. Oh, no, I'm sorry. So that line here is supposed to be showing, I'm sorry, there used to be a line there. And this is basically saying which word you want. Okay, bits 2 and 3. Okay, just a clarification. Okay, let me keep going, actually. So, all right, so we talked about this already. This is a figure out of the book, which is at some point, if your blocks get too big, your argument might think that bigger blocks are always better. And what this is showing is for different cache sizes, what happens to the miss rate for this particular workload as you increase the block size. So the cache stays the same size, and you increase the block size. And what you find out is, in most of these cases, there's kind of a sweet spot where your hit rate gets better, okay, as you make the block bigger, but then after a while, the hit rate starts getting worse again, okay? And the reason again for that is, as you're making the block bigger, you're taking advantage of spatial locality, okay? But at some point, the extra benefit you get of making that block bigger starts decreasing, and what ends up happening is the cost of not being able to keep as many different blocks in the cache is starting to hurt you, okay? So you get this sort of characteristic shape of there being a sweet spot for a given cache size of what the right amount of data you should have in each entry is, okay? So just keep that in mind, and that's described a little more in the book. Okay, so we talked about reads and writes, and we spent most of the time right now talking about reads. Writes have similar behavior in some ways, but there's some special things you have to worry about, okay? So right now we've been basically pulling data up from the memory, all right, or the lower cache levels to the processor, okay? When you do a store, you got to go the other way, right? Because you're going to make an update to something in memory. Okay, so the question is, how do you do that? All right? And the trick is, you need to either keep your cache always consistent with the memory, meaning that if you have a cached value if you have a cached value sitting in your cache, that it's got the same exact data as what's sitting in memory, right? Or if you're not going to do that, you have to be very careful, okay? So those are really our 2 choices here. The first choice is what's called a write-through policy, which just basically says, when you do that store goes into the cache and then gets written right out to the memory, okay? So you never have this chance of there being an inconsistency. Okay, the next time somebody tries to read memory, they'll get the same exact value that's in the cache. And now, you got to be a little careful because remember, memory is really, really slow. So if you really did that write-through on every store, your system would get very, very slow. And so if you're going to do write-through, typically what you do is you write through to a buffer. Okay, and a buffer is a special place that you put it there. It's fast to put it there, and the system guarantees that, hey, eventually I will write this thing from the buffer out, so don't you worry about it. In which case, when you do that write to the cache, goes to the buffer, you can keep going, okay? Except if the buffer's full, then you got to wait. You got to wait until the buffer gets emptied a little bit, and then you can do your write to the buffer. Yeah?
Does it take
Does it take...
Or is it linear in time, or
So
each trip takes
writing to memory is not exactly linear, but certainly, if you're updating multiple bytes in a word, you're better off doing those all at once, right? You can do those in one shot. So that's kind of the big, you get sort of a step function, which is you want to save up as much stuff as you can write in a single chunk and then write it. Okay? Yeah.
So if you use the right buffer, does that mean that it's possible that sometimes you access the memory too soon?
If you use the write buffer, you have to make sure that all your accesses are going through the cache. That's right. Okay, because there will be a time when the updated data might be in the cache and the write buffer, but not in memory yet. But the way our memory system is set up is we always go through the cache. So this gets more complicated if for some reason, if you've got a multi-core system and you've got multiple caches, then you've got a cache consistency problem. That's beyond what we're going to talk about. So we're assuming a single cache. Yeah.
What if you overwrite the cache while you're writing the memory buffer, and then you try to access the memory again?
Okay, so the question is, what if you overwrite the cache while the write is in the write buffer? So the rule is, you always read from the cache. If it's in the cache, you read it. You have to make sure, there is a timing thing I could imagine where you've thrown something out of the cache, it's still in the write buffer. I guess you have to make sure that, if it's in the write buffer, you get it from there. Yeah. So, or you force it to memory, that it can get out to memory. There has to be a little handshake there. Good. Yeah, these are all the subtleties, and as we said, it gets worse with multiple cores and all that. We're trying to do simple cases here. The thing that's usually considered more efficient, although actually even more complicated than the write-through, is what's called a write-back policy. And what you do in a write-back policy, it's what's called a lazy approach. Okay, so write-through is eager. It says as soon as that write happens, as soon as that store happens, I'm going to initiate all my writing mechanisms. Okay? Write-back says, no, I'm going to be a little lazy about it. And what I'm going to do is I'm going to keep the update in the cache, not worry about writing it out to memory, and then when that data gets replaced from the cache, then I'll write it out. Okay? So in order to make this work, you have to have a little more information. So if you remember before, we had our data, right, and we had our tag, and we had a valid bit, which just said is what's in the entry real data or not. Now you have to add an additional bit called the dirty bit, which is the data that's at this entry, has this been updated and not written back to memory yet? Okay? And if that bit is on, then when you go to replace the data that's at that entry, you first have to write it out to disk, either to a write buffer or directly to memory if you don't have a write buffer. Okay? So if you think about it, what the write-back policy is doing is, again, it's trying to take advantage of some notion of temporal locality, right? Which says, if I just updated this memory location, I'm probably going to update it again. Okay, so why write it out just to overwrite it again, in a couple more instructions? Okay, so you just basically keep the updates in the cache. You set a little flag that says, hey, when you replace this thing, you can't just clobber it. You have to write it out to memory. And the system takes care of that when that replacement happens. Okay? So eager is the write-through approach. Lazy is the write-back approach. Okay? So, okay, good. So let's try to put all that together. So we talked about what happens on a, let's talk about cache hits. So on a read hit, we've talked about that in some amount of detail, right? Where we, you do the lookup and you just return the data. And, hits are important because that's going to make us go fast. We don't have to go to memory when we get a cache hit. Okay? And read hits can happen in the instruction cache and in the data cache. Okay? Write hits, meaning you're going to do a store, right? And that store is going to go through the cache. That can only happen in the data cache, right? Because you're not allowed to update the instructions on the fly. Okay? So write hits only happen when there's only happen to the data cache. And basically, you have these two choices, the write through, okay, which is the eager approach, which says I'm going to write it out directly, either write to memory, which is going to take me a while, or to a write buffer. Or I'm going to use this write back approach, which says, I'll just set the dirty bit and make sure when I replace that entry, I do the write then. Okay? So that's that. What about misses? So those are hits. What about misses? So let's talk about single word blocks first. Okay? So for read misses, again, those can happen in both the instruction cache and the data cache. What you do on a miss is really bad. You say, stop the processor. Okay? Go out to the next level of memory, of the hierarchy. Hopefully it's not memory. Hopefully it's your level 2 cache. Okay? But go out there, see if the thing's in there and get it, and just get it for me. I don't care where you get it from. And I'm going to wait till you give it to me. Okay? So that's what slows things down. Write misses, you have a couple different choices. You have a few different choices. So now you're going to do a load, and the thing that you want to write to, you want to do a store. The thing that you want to write to is not in the cache, so what do? So one thing you could do is you can go get the data. Okay, so you can bring the data in. Okay, so basically just like you would on a read miss. Then you update it and set the dirty bit. Okay, and then depending on whether you're doing write through or write back, that determines what happens after that. Okay, but in a single word block case, you don't actually have to do that. You can actually just write directly into the cache, right? Because what we did in that previous step is we said, okay, read the word in and then write over it. Okay, so you could say, all right, I don't have to do that. What I'm going to do is I'm just going to pretend that the thing is already in the cache line. First, I'm going to check to make sure that the thing, I'm going to write into the cache at the entry where this thing needs to be. So first you check to see, is there something marked dirty there? If there is, then you got to write it out. If not, then you just write the new value into that cache entry. Okay, that's called write allocate. And then no write allocate just says that, okay, I'm not even going to write it into the cache. I'm just going to write it directly out to memory or into the write buffer and out to memory. Okay, so those are your choices on write misses. Okay, for a single word block. Okay, multi-word block, it gets slightly more complicated because it takes a while, as we were talking about earlier, to read in multiple words from the next level. Okay, so when you miss on a multi-word cache, you have to go get that entire block. And then there's a question of whether you can start processing as soon as the word that you're waiting for comes in, or do you have to wait for the whole thing? And then some systems are smart enough to send the word that you actually requested before the rest of them. Okay? And then there's something called a non-blocking cache that lets you handle one request while you're doing other things in the cache. So you don't have to do just one thing at a time. Okay? Multi-word writes, you don't have that option of just clobbering what was in the cache because you're only writing one word, okay? And the thing you're writing into might actually be data from a different address. So what you have to do there is you actually have to go do that read, right? Read the data, read that whole block into the cache, and then do the update of that word that you're updating, okay? And so that's the slight difference there. All right. So what's left to do today, which I'm not going to be able to do, is we're then going to take this whole set of concepts we've come up with, and we're going to say, okay, what does that really do to performance? That's what the Moneyball thing was supposed to be about. And we're going to come up with the right metrics for determining that, and then we're going to talk about one or two more optimizations for the cache, and we should be done with that on Wednesday. So that's all we got for today. Thanks.